moving on from there. So the next thing to think about is, how do we optimize the code for this polling loop? How would we do that? Well, here's the code. The first thing we could do is move this outside and move this loop down here. So it just branches here, because once we've set up this address as a pointer, we could just use it. But do we really want to bother? We're still going to be here, and really here is a very busy loop just waiting for a key to be pressed. So we could very slightly optimize it. So let's look at this then. What we've talked about is the fact that we'll, with polling, be in this busy waiting state where we keep checking to see if a key's been pressed by comparing a particular bit, bit 7, and seeing if it gets set. So we're going to, well, carry on in this polling loop. And really, the computer or the CPU can't do anything else. Is that a good thing? But in reality, we might want to do several other things, and we might want to do these one after the other, such as, when you hear this, it's really telling you you've got to write some notes down. It's only a very brief note. In this case, but we want it to do several things at once, and one of them is to look after several peripherals. We also might have to run a program instead of being in this wait loop. So what we're really seeing is the CPU must respond to other events. So let's have a look at this then. It must respond to events while a program is running. And really it's got to respond to a number of things. Maybe an input from another peripheral that is telling it, I'm ready. Or it needs to output data to an output peripheral because its data register, via its status register, has told it, I've transferred that data now. And finally, if something happens to a program, maybe we've got to deal with it. Or maybe a timer goes off. So maybe sitting in this busy waiting polling loop isn't a good idea because it takes up CPU time. So now we're going to move on from polling to interrupts. So we've got a puzzle then. How do we stop this polling program taking up all the CPU time, because it's going to sit in the busy waiting loop? Say, for example, we were running an animation program that must keep having input from a user. So we have a keyboard and we have someone that needs to, well, really interact with this animation. So the keyboard could be, if you like, prodding the CPU when a user types a key. So when a key is typed on the keyboard, we need to go through a number of steps. In fact, when a key is typed, we need to follow 3 steps. So let's look at the first one. So again, this is telling you you have to add a note to your lecture notes. And that is, the first thing we're going to have to do is pause the present program. So pause the program. The second step is get the character, and then we resume the program. So as you can see, pause, get character, go back and rerun the program. Might not quite be as simple as that. We'll see in the next few slides. So the answer to this then is, really, maybe it'd be better if the peripheral initiated this action of transfer. And that's actually what interrupts do. The peripheral interrupts the processor, as opposed to the processor polling the peripheral. So let's have a look at the detailed sequence of events for an interrupt. So a program's already running, and that's normal on computers. So in this case, we're sort of in a moderate state. We're running a program. So let's undertake 5 steps to handle an interrupt. So what we're talking about here is a peripheral interrupts a CPU, and basically we have 5 steps to go through the process of handling it and then giving back the initial program the CPU to run its program. The first thing we've got to do, number one, is stop the program that's running. But we can't just stop it, we have to do a bit more. So the next thing we have to do is save all the working information which is stored in the registers, and even maybe the conditions code. So we'll see that in a minute in a bit more detail. Stop first. 2 save registers. 3, we can then run the interrupt, and we do this by running what's called a handler. So that's a naming convention for a bit of program that handles the interrupt, specifically an interrupt handler, which is a method or bit of code to interact with the peripheral. And then once we've run that program, it's undertaken the transfer, we restore all the registers we saved from the previous program, and then finally 5, we set the programming going again so it continues. So 5 steps for undertaking and transferring control from a standard program to an interrupt handler. So what does an interrupt handler basically look like? Well, really an interrupt is something like a branch and link, and as you're aware of, a branch and link does a branch, but it also saves down the address for when you return back from the branch, so you return to the next instruction after the branch, and it returns this and saves it in what's called the link register. So the interrupt, as we're aware now, has to be handled. But the first step is storing any registers. Maybe R0 and R1 have values in that the program that's presently running requires. Now if we don't save these down, we could get errors when we come back because that data that's needed is now lost. So that's why we save down the registers. But we also save down other things that the program might be using, like status that's been set up on our conditions flag. So this is really saying we basically must save the status register. In the ARM sense, we save the current program status register, and we must remember all these, because if we're going to do any future tests or compares in the next few lines of the program, that's why we need to save the status register. Now if we look at this, ARM has a number of other registers as well, which we're going to probably save down and use to do this process. One of them is the link register. As we've seen, we use this in the equivalent instruction to an interrupt, which is branch and link, because we're going to save the link register, which is the address of the next instruction after the interrupt. And we might need, as it says there, to save a stack pointer, and even, as we've just seen, save the current program status register, which saves the program status register. So we need to do all of this so we can hand over to the interrupt. So we can then save them down and then restore them. The present context of the presently running program. So now let's go and look at a very simple interrupt handler. So we're going to step through this relatively slowly, and you see it's got a number of areas. We've broken it down into chunks. The first one saves down our registers, so we're going to set them up first just to show you once we've saved them and basically restored them, we can see that the data we did save is actually restored. Now the other things we're going to do in an interrupt is, first, there's slightly difference between polling and interrupts. So in the case of a status register in an interrupt, we just want to double check that the interrupt is correct. If it's not, it shouldn't have interrupted and will actually branch to an error. So we still will investigate in the first chunk of code and look at the status register. Then we're going to move on to reading the data and place it somewhere, and then we may have to acknowledge it and tell the peripheral we've actually done it. Let's jump into the code now and see what happens. So moving through, the first thing we're going to do is we're going to actually load some data into register 0 and register 1, just so you can see when they're restored, this data will be restored. So let's just put values 1 and 2 in registers 0 and 1. So let's step through the first. We're going to load instantaneously or immediately 1 into R0. In our next instruction we're going to load 1 into R1. So let's step through that instruction. We've now loaded R1 with 2. Now we're going to simulate the interrupt. So we simulate it by jumping to a very basic interrupt program. They're really a bit more complicated than this. So let's undertake the interrupt now. So we now jump to the interrupt. We've saved down some information into the link register where we were, and the first thing that happens is we're going to save the register 0 and register 1. So we save the current workspace. So let's step through that instruction. Now, as we did before, we're now moving on and loading register 1 with the address as it's memory mapped of the status register. So let's step through that. So we now step through, and this is the address of the status register. We now use R1 as a pointer to the data in the status register, and we load LDR byte the register R0 with the actual status register data. So let's do that now. So we've loaded the data into R0. We're now going to interrogate it by using this test. If you remember, it's equivalent to the AND operation. So let's step through this and maybe the best way to do this is to see if or if not it sets up this 0 flag in the conditions register. So we'll step through this instruction TST, and we see straight away that it doesn't set the 0, so it is telling us that this R0 and the bit pattern are the same. So if it wasn't the case, we'd have an error, but we don't. And this bit of code here is just to say, well, it's taken the view that polling the CPU controlled the process, so it wasn't an error. But in this case, as it's a peripheral, the peripheral has interrupted the CPU, so we're checking the status register. The bit should be set. If it's not, there is an error. We would have to write a bit of code to deal with that. But we see now, due to this condition setting, that it's 0, we branch equal, and we're going to step through because it is equal to 0, and now read the next chunk of code which will read the data register. So we've got to go through the same process. First, read into R1 the address of the data register. So R1 has now changed to the address of the data register. Now what we do is use R1 as a pointer, point at the address, the memory mapping location of the data register in memory, and load R0 with the data in the data register. So we've now loaded again, it's capital H, into R0. Now the difference here is we're actually going to show you that we save it somewhere. So we need to load the address of where we're going to save it, so we're just going to save it somewhere and put the address into R2. So stepping through this, we'll put the address here where we're going to save it. R2 is then used as a pointer, and we store this data using the str, store the data in R0. Now we're stepping into the chunk of code that will acknowledge the peripheral and tell it we've undertaken that transfer. So first we load the address of the acknowledge register that's memory mapped into R1. So now we've got the acknowledge register memory mapped address there. Then we use it after loading R0 with 1, and we use R1 now as a pointer and store the 1 in that location. Now we retrieve a number of things from the stack. We retrieve R0 and R1, so you're going to see these change in a second because we'll retrieve the previous data. And now we have to restore the program counter and move back from the subroutine, which is an interrupt, back to where we were before. And you'll see now that these two registers have been restored.